So before we actually get into chapter 2 today, I just want to do a little introduction about what this course is about, where we're going to go with it, and just introduce you to the concepts of biology in general. So this is biology. Hopefully, you guys, as we you signed up for it, so hopefully you know what it is. It's the study of what? Of what? Life. There we go. Life. So life is a small word, but it has a big meaning. So there's, it's really kind of hard to define what life is. So we want to start by looking at that a little bit. And as I said, a few things from chapter 1. Now, chapter 1 I did not put on your syllabus as a required chapter, but there are a couple introductory things I want to go over just as an FYI, and then we'll get into chapter 2. And again, on the course outline, that's going to be that will be page 5. Okay, so to introduce biology, I'm just going to start with this video, and the video is, it doesn't have any narration, so you have to read it, but it's got great footage, so I think you'll really appreciate it, so let's start with that.
Writing's not that easy.
Well, this is new.
She's on pause.
Oh, thank you. Wake up. All right, try that again. One more. There we go. Okay, so as I said, we're gonna start with just kind of an introduction into what is biology. And when you define, we said that biology is the study of what again? Life, right? And so when we try to define life, it gets kind of complicated. If you're a philosopher, you might define it one way, but if you're a biologist, you usually define it based on comparing it to non-life. So if I'm comparing you, which you guys are all alive, right, to this table, which is considered non-living, what's the difference? And so we usually sum it up in terms of 5 attributes that all living things have in common. And so you saw on that video clip all kinds of living things. And so what are all living things made of? What is the smallest unit of life? Anybody know? The cell, exactly. And so we start there looking at the cell and what do all cells do that make them considered alive? Or what do we all do that we all have in common? All living things. When I say all living things, I mean not just people, but plants, animals, fungus, all of that. So anybody have any? What do all living things do? Yeah.
We digest food and get some sort of energy and use it.
Absolutely. So she said we digest food, we get some sort of energy and use it. And so how do we get that food? A lot of times people say, well, all living things eat. Well, eating is kind of a mechanical process. So all living things don't actually chew up their food and swallow it like plants do take in nutrients, but it's in the form of fertilizer, right? So all living things don't necessarily eat, but they all do take in nutrients. And as you said, the reason we take in nutrients, and you might also say, well, all living things breathe. Well, breathing again is mechanical, inhaling and exhaling. And plants don't do that, but they do have gas exchange, right? So in photosynthesis and respiration, we're going to study those processes. We're going to see how those gases are exchanged. And so all living things take in gases, they take in nutrients, and they cash it all in for, as you said, energy. And there's one word for that that describes that whole thing. It begins with an M. Anybody know what it is? Everyone's worried about trying to ramp up their metabolism. Exactly. So all living things metabolize. That's a big one. We spend quite a bit of time talking about metabolism and how it goes on in the cell. And if you understand that, you understand the big picture, that is your metabolism and how you can get it to do what you want to do. So this course is all about really looking at how all these processes affect you because you are alive, right? So metabolism, what else do all living things do? Anybody? Yes. Reproduce, absolutely. Even on the cellular level, one cell divides into two, two into four. All living things reproduce, and that we will see in mitosis and meiosis how cells reproduce. And there is one more big one, so they all metabolize, they all reproduce. What's the difference between you now and when you were born? What did you do? Grow, exactly. So all living things grow. So those are the top 3 that we focus on in this class. And looking at, especially from the cellular level, how cells grow, reproduce, and metabolize. Now there's 2 others I'm going to add to this list, and they are not quite as common, not something you're probably as familiar with, but all living things display something called irritability. And when I say that, I don't mean that how you felt this morning when you woke up, when your alarm clock went off, and maybe you were irritable. That's a different kind. When we talk about this kind of irritability, we're talking about the fact that our cells and ultimately we can make quick-term responses to changes in the environment. So for instance, if I turn the lights out, what would happen to your pupils? They get bigger, right? They dilate, they let more light in. And then if I turn the lights back off, if I turn them off, they get bigger. If I turn them on, then they're going to constrict, right, and try to filter out the light. So we're constantly adjusting to the changes in our environment. And in fact, every time you eat or drink something, you change your body chemistry. Your body has a lot of work to do when you feed it because it's got to decide where to make a lot of decisions about how to process that food and where it's going to go. So you're always changing, and our bodies are really dynamic. They're constantly in flux. So that's irritability, and over a long period of time, we have to adapt to our environment. Otherwise, we don't stay alive, right? If the polar bear in the Arctic didn't have a nice heavy fur coat, he couldn't adapt to that environment. And the Florida black bear has a leaner coat and can handle the heat. So most organisms, with the exception of us, have to adapt to their environment. We have managed to adapt our environment to us. So we have air conditioning, we can adjust the light, we can change it if it's cold out, put the heat on. So we can have this internal environment so that we can adapt that is to all different kinds of climates. So if you study anatomy and physiology, you spend a lot of time talking about how your body changes and responds to changes in the environment. And if you study either environmental science or ecology or even in Bio 2, we talk more about adaptability. But in this course, as I said, we're going to focus on the top 3. So if you were to go back in chapter 1, as I said, there's a couple things out there I just wanted to mention before we get into the meat of the course. And that is, where we're going with this course. Well, we said the smallest unit of life is what? It's the cell, and here's a cell. We're going to spend a lot of time in lab looking at cells, studying cells in lecture as well. And cells are made up of cell organelles. We're going to spend some time looking at all these cell organelles, which are made up of atoms and molecules. So here's the thing, if life starts here, are organelles, atoms, and molecules considered living or non-living? Since they're subcellular, can they grow, reproduce, and metabolize on their own? No, so they're non-living, right? So life begins here. So sometimes people ask me, well, why are we studying chemistry if this is biology? Well, we're going to study what is more known, often called biochemistry, and that is the chemistry of life. So we have to understand really how atoms form molecules and those form the cell organelles before we can understand the cell. So that's where we begin in this course at that point in chapter 2. And if you were to go on and continue studying this, you might take anatomy and physiology, where you would look at how these cells come together. Groups of similar cells make tissues, and those tissues make organs and organ systems. And that makes the organism, so you might study that. If you were going to just study single-celled organisms, that's what you do primarily in microbiology. And then if you're going to this higher level area where maybe in Bio 2, for instance, we look at how organisms come together of similar species to make up populations, and then add different species and you get a community, and then add all that with the physical environment and you get an ecosystem, and ultimately everything in the biosphere. So those are things you might study again in environmental science, ecology, or Bio 2. So again, we're just really primarily focusing on cell biology in this course. And that brings us then to chapter 2 outline, the chemistry of life. And there are a lot of terms in this course, folks. And I mentioned the first day of class that you might want to do flashcards before you come. If you're not familiar with these terms, get familiar, because once I define all of these terms, I start talking about them as though you understand what I'm saying. So you shouldn't be hearing this for the first time when you walk into lecture. So that's a really good way to study before you come to class. So let's start with a general definition of matter. Organisms are composed of matter. How do we define matter? It's anything that what? Takes up space and has mass, exactly. And that's kind of everything. In fact, what about the air? The air, is this matter? Does it have mass and take up space? Have you ever picked up a tank of air? Any scuba divers in here? It's heavy, right? It's definitely got mass. And so just because you can't see it doesn't mean it is not matter. So it's anything that has space, or that has mass and takes up space. And so that's kind of everything, really, with the exception of one other thing, which is energy. Anybody know what energy is? The ability to do, this is just throw it out there because we haven't gotten there yet, but yeah. To work, exactly, or cause change. Some people define it as that. So, so really, you know, we used to kind of keep these separate. You've got matter over here and energy over here, but now physicists sort of see that they all work together. They're kind of jumbled together. But we're going to take a first look at how matter, specifically on the atomic level, affects cells, and then we'll get to energy as well. So when we look at matter, then that brings up a couple of other terms: element, molecule, and compound. And these are all defined for you on page 5 of the course outline. So what's the difference? It says here an element is a substance that cannot be broken down to other substances by chemical reactions. So it's kind of a pure substance, and in fact, it's so pure that we have a table of elements up here. This is something you've probably seen if you've ever had chemistry. And in this course, we don't really need this big chart. In fact, on page 10, I've given you a simplified version of the periodic table of elements that we're going to use in this class. It really just focuses on the elements that are important to life. And so you might want to get that out if you have your outline. We're going to be using that throughout the lecture today. So an element is a pure substance, and it's made up of the same kind of atoms as we're going to see. And a molecule compared to a compound, what's the difference there? A molecule is an electrically neutral group of two or more atoms held together by chemical bonds, and a compound is a substance consisting of two or more elements. Well, it sounds kind of like the same thing, so what's the difference? Let's take something like water. Anybody know what the chemical formula for water is? H2O, right? H2O. And if we put this in a structural formula, it's going to look like this. There's two hydrogens attached to an oxygen. So this is what? A molecule or a compound? Compound? I'm going to say molecule. Have you ever heard of a water molecule? That sounds right. So, right, it's kind of a trick question because it's actually both. So if we take it just like this unique molecule that likes to stick together and it's hard to even separate the hydrogens from oxygen, that's a water molecule. But if I put a whole bunch together in a glass of water, then you would have a compound. So the big difference, I guess, would be a molecule is kind of the smallest part of that compound, that unique molecule that sticks together. But as the definition says, it's two or more elements. So we've got two elements here, hydrogen and oxygen. By the way, when you see a little 2 like this means 2 atoms of hydrogen, and if you don't have a 1, any number here, you assume it's 1. 1 atom of oxygen. And if I put a 2 up here, that would be 2 water molecules. So again, a subtle difference. Sometimes people use these interchangeably, but so the answer is kind of both. So that brings us then to looking at, if you have your book with you, page 29, has a table of the elements of the human body. And as you can see in this table, that over 96% of our body mass, including water, is made up of these 4 elements: oxygen, carbon, hydrogen, and nitrogen. And in fact, what we are really are a bunch of hydrocarbons. And so we see we've got these long chains of carbons, and then we have hydrogens attached. So that's a hydrocarbon. So those are the 2. And then often attached to those, we're going to see nitrogen and oxygen. So that makes up most of our body mass. However, even though less than 4% are these other elements, they're still extremely important to life. So things like calcium, why do you need calcium? Bones, exactly. And how about sodium and chlorine? That makes sodium chloride, which is what? Table salt. Do you need salt to stay alive? Absolutely. Too much salt is no good, right? But you definitely have to have some salts. And so a lot of these do make up salts, and we'll spend some time talking about why those are so important in the body. If you've ever gone to the doctor and had your electrolytes checked, and they find out, there's an imbalance, that's a problem. That's a salt problem. And then we have these trace elements that are found in less than 0.01%. That's teeny tiny amounts. And yet still, if you don't have them, it can cause death. And so these are really, really important as well. So those are the elements important to life. Those are the ones that I have on your periodic chart that we're going to be using in this class, and also that's going to be your reference on the first test. So you definitely want to have that. It will be on the test though, printed. You don't have to bring that one. So let's go to concept 2.2, still on the course outline, looking at page 5, and talk about an element's properties. And it depends on, as you see there, the structure of its atom. So first of all, what is an atom? Anyone know the definition of an atom? Smallest particle of matter. Matter. So we said matter is anything that has mass and occupies space, and if we break it all down to the very smallest component, that's an atom. And yet, An atom has even smaller particles, and you might know the big three. Anybody remember the big three? Protons, neutrons, and electrons, right? And now we know that there are gluons and quarks and a whole bunch of other stuff there, but we're gonna stick with the basic three subatomic particles, protons, neutrons, and electrons, and look at how they affect the properties of an atom. But first, this clip on atomic structure.
Please comfort me. Atoms are divided into two major parts: a centrally located nucleus that contains positively charged protons and uncharged neutrons, and one or more orbitals, regions in the space surrounding the nucleus in which negatively charged particles, called electrons, travel about continuously at nearly the speed of light. Protons and neutrons each have a mass approximately 1,836 times greater than that of electrons. However, in spite of the huge difference in mass between protons and electrons, their electrical charges, though opposite, are equal in magnitude. As atoms have equal numbers of protons and electrons, they are electrically neutral. Every element has a unique atomic number. The atomic number of an element corresponds to the number of protons found in the nuclei of its atoms. For example, hydrogen atoms have one proton and an atomic number of 1. Helium atoms have 2 protons and an atomic number of 2. While carbon atoms, which form the atomic skeleton of all the larger molecules found in living organisms, have 6 protons in their nucleus, giving them an atomic number of 6. While every atom of a given element has the same number of protons, the number of neutrons contained in the nucleus of atoms of the same element can vary. For example, carbon atoms can have 4, 5, 6, 7, 8, or 9 neutrons. Each of these different forms of carbon is referred to as an isotope. Isotopes of a given element like carbon are virtually identical to one another in terms of chemical reactivity, but sometimes vary in their physical properties. For example, the nuclei of some isotopes, called radioactive isotopes, spontaneously disintegrate, releasing radiation in the process. In the case of carbon, the isotopes carbon-12 and 13 are stable, while carbon isotopes 10, 11, 14, and 15 are radioactive. The existence of radioactive isotopes in carbon and other elements allows scientists to carry out tasks as different as digging the fossil remains of long-dead organisms to study the physiology of the human mind. However, it is the behavior of electrons in an atom's outer orbitals that determines how the ions and molecules critical to life are formed.
Oh.
What's it say?
No, I'm asking that. That's stuck.
It's all right. Okay, so just a reminder that I am videotaping these, video capturing these lectures for a hybrid class. So if you must come up in the middle of class, just please do not bump that camera or I'll have to stop everything and fix it. So I would prefer that you come up before or after class, that would be more helpful. Also, so back to concept, oops, we did that. Let's go to then on page 6 of your course outline, talking about these subatomic particles. So we saw in that clip there are 3 subatomic particles, protons, neutrons, and electrons. Which ones have a positive charge? Protons. Which ones have a negative charge? Electrons. And then, of course, neutrons are neutral. 2 of them are found in the nucleus. Which 2 are found in the nucleus? Protons and neutrons. And notice they have what we call an atomic mass unit, which is kind of a relative number or weight. Mass is similar to weight of 1. And so the reason that they both have an atomic mass unit of 1, whereas the electrons have an atomic mass unit of 0, is because electrons are relatively weightless. Now, they do have mass and occupy space, so they are matter, but they're so light they just give them this relative number of 0 compared to protons and neutrons, which are about the same size and same weight, and we give them an atomic mass unit of 1 then. So when we're looking at the physical properties of an atom, we want to look primarily at the protons and neutrons because they are the ones that have mass. Whereas the electrons, even though they're relatively weightless, they are very important, but more from an energy standpoint. So we'll come back to those and talk more about those. But for now, we want to spend time looking at, again, the physical properties of an atom. And so with that, we have some more terms. We have atomic number versus atomic mass. Again, you're going to see that word mass used interchangeably with weight. You might hear it called atomic weight. And really, unless you're into physics, there's not a huge difference. It has to do with gravitational pull. So we're not going to really get too split hairs about that. But so what is the difference between atomic number and atomic weight or mass? So atomic number is defined as the number of what? Protons, okay? And that's how we define an atom. It's always based on the number of protons. So when we look at your periodic chart, and again, you want to have that out, and over on page 10, you can see that the top number shows you the atomic number in any one of those elements. And then the bottom number shows you the atomic weight, as it's called there, or mass, as it's called here. So the atomic weight is a number of what? How do we define the weight? Protons plus neutrons. So here's the thing, folks. If the weight is protons and neutrons and the number is just protons, if I subtract the 2, what do I get? Taking the protons out of the protons and neutrons, that would leave me neutrons. So when I have a periodic chart, I can figure out the number of protons, neutrons, and electrons in any one of these elements by looking at the chart. So just a couple things about this chart that we see. First of all, in dark blue, we've got hydrogen, carbon, nitrogen, and oxygen. Those are the top 4 elements that make up living organisms. And then we have in light blue some of those important elements that make up salts and other important elements to life, and then we have all the other ones. So this simplified periodic chart is really just focusing on the elements that are important to life. So how do we find the number of protons, neutrons, and electrons in any one of these elements? Well, we just look at the top number. The top number tells us the number of what? Protons. The bottom number tells us protons and neutrons, so if I subtract the 2, what do I get? Neutrons. And then how do we find electrons? By definition, an atom is electrically neutral. So we said protons have what kind of charge? Positive. And electrons have what kind of charge? Negative. So if we had an element that had 6 protons, how many electrons would it have to be electrically neutral? 6. That makes it a net charge of 0, right? So here's the thing, that top number, the number of protons, also is the same as the number of electrons. And then we subtract the 2, and what do we get? Neutrons. So let's try a couple of these. This is something that will be on your first test. giving you this chart and asking you, if I give you any element that you see in this chart, give me the number of protons, neutrons, and electrons. So here's the symbol, and I want to know the number of protons, neutrons, and electrons in any one of these. Let's start with lithium. Lithium, as you see there, as the top number is 3, the bottom number is 7. Top number again is your atomic number, which is the number of protons. Bottom number is 7, the atomic weight. So everybody take a minute and write down the number of protons, neutrons, and electrons that you find in lithium. Okay, so top number is the number of protons, and lithium has how many protons? 3, which is also equal to the number of what? Electrons. We subtract the 2, right? 3 from 7, and we get how many neutrons? 4. Good. Okay, let's try one more. Let's try sodium. Right below that. Sodium, top number is 11, bottom number is 23. Okay, how many protons? 11. How many neutrons? 12. We subtracted 2, and remember electrons are the same as protons, so 11. Notice that these two numbers are always going to be the same, right? And the way you find the middle number is subtracting the top and the bottom. Everybody good with that? Do I need to do another? So what you should do as practice before you take the first test is go through all these elements and finish this chart. Just keep practicing how many protons, neutrons, and electrons. And then once you get this chart all written out, then put away your table. And given the number of protons, neutrons, and electrons, tell me the atomic number and atomic weight. Because if I give you the number of protons, neutrons, and electrons, the atomic number is the number of what again? Protons. And for weight, I would add up what? Protons and neutrons, exactly. So let's look at this next slide. What is the atomic number of this atom? So look at this. This is what we call an electron shell diagram. It's showing us the two atomic particles that are found in the nucleus here. The pink are showing you the protons with their positive charge. The neutrons are shown there with no charge because they're neutral. They're shown there in brown. And then the electrons, notice, are orbiting around this atom in what we call an electron shell. We're not really paying attention to those right now. We're going to come back to them. But as far as the atomic number, we said the atomic number is the number of what again? Protons. So how many protons do we have in this atom? 2. See the 2 pinks? Okay. And so that's the atomic number. What is the atomic mass? What do you have to add to get the mass? Protons and neutrons. So what's the mass of this atom? 4. What element is this? How would I find out? What number do I look up to determine what element it is? The atomic number or the atomic weight? It's the number, exactly. So look up in your chart and find out which one has an atomic number of 2. And tell me what you get. Helium, exactly. So this element is helium. Okay, good job. Notice again, the protons, the positive charge, and the electrons balance out. If you have 2 protons, you've got to have 2 electrons to balance it out. Because by definition, atoms are electrically neutral. Okay, there's another, try this in your outline. This is on page 6. And it asks you, given the number of protons, neutrons, and electrons, find the atomic number and atomic mass of each of these elements. So take a minute and look at element X, find the atomic number of element X and Y, find the atomic mass of element X and Y, and then see if you can answer this last question. Okay, so what'd you get for the atomic number of element X? 6, right? Because remember the atomic number is the number of protons, and it's got 6 protons. How about the atomic number for element Y? Also 6. How about the atomic mass of each element? So element X has 6 protons, 6 neutrons, so what's its mass? 12. And element Y has 6 protons, 8 neutrons, so it is what? 14. Are these different elements? How do we define an element? Based on atomic number, right? So since they both have the same atomic number, are they different elements? No. In fact, what element is this? What element has an atomic number of 6? Carbon, exactly. So what these are, anybody know what we call these when you have the same element but different weights? Isotopes, exactly. So we have carbon 12 and carbon 14. So what's the difference between carbon 12 and carbon 14? Well, which one's heavier? Carbon 14 because it has 2 additional what? Neutrons. Exactly. So it's the same element but different numbers of neutrons or different weights, and that's what we call isotopes. Exactly. So how do we define an isotope? Again, all atoms of an element have the same number of protons but may differ in their number of neutrons. So isotopes are 2 atoms of an element that differ in the number of neutrons. And we have all kinds of isotopes out there, and some of them are very, very heavy. And in fact, if you've ever heard of uranium, what do you think of when you think of uranium? Anybody? Nuclear power, nuclear bombs, that's what they use to fuel it. And these are heavy isotopes, uranium-235 and 238. That means they have 235 or 238 protons and neutrons. That's pretty big for an atom. And so what we do is we take that uranium, that's fuel rods, we put it in a nuclear power plant, we hit it with a neutron, it breaks it up, it starts a chain reaction, and every time it splits that atom, it then breaks it down and changes the number of protons, which means that's how we get man-made elements, by splitting these atoms. But every time we do that, we release a tremendous amount of heat, and that heat is used to heat water that turns to steam, that turns a turbine and gets electrons flowing, and that's electricity. So it's a great source of power for electricity. The problem is that after a while, the reaction stops and you don't have enough energy to continue the process, and now we have what's called spent fuel. And unfortunately, it's radioactive. Radioactive isotopes are giving off subatomic particles that can travel so fast that they can penetrate your skin, sometimes they can penetrate your cells, sometimes they can get into your DNA and change it and cause mutations that can lead to cancers and all that. That's why we don't want to be exposed to too much radiation. So what do you do with that? And that's always been a big problem with nuclear power is, where do you put the spent fuel? Nobody wants it in their backyard. So go bury it in Utah somewhere. I don't think those people would be happy with it either. Nobody wants too much radiation. However, radioactive isotopes can be used to do a lot of important things. We use them in applications that require dating, things like dating fossils. We can trace atoms through metabolic processes and use them in imaging and diagnostic procedures in the medical field. Radiotherapy, I'm sure almost every one of you has been somebody or heard of somebody being on radiation for cancer. They actually expose the tumors, hit them with radiation, and that will kill those cells. So it would hopefully not expose the rest of the good cells to that radiation. That's always a problem with radiotherapy. Nuclear medicine also uses radiation to provide diagnostic information and, for example, to find tumors. As it turns out, tumors are growing very, very quickly. These are cells that are growing so fast, and because they're growing so fast, they need more energy than all the other cells. And anybody know what our main source of energy is in our diet? If you want quick energy, what are you going to eat? Carbs, sugar, right? And so what they do here is they use a small amount of radioactive sugar that's injected into the bloodstream, and they will absorb it, and then it will give off these light particles known as photons, and you can actually see the tumor that way. So that's how we use a PET scan. This is the reason they say there are some theories that say if you are diagnosed with cancer, you should stay away from sugar because you're just feeding the cancer cells. So they are going to be sucking it up faster than other cells according to that theory. But here is how a PET scan works. And this is a really important branch of medicine, by the way. If you guys are thinking about going into the medical field, you might want to think about nuclear medicine.
A PET scan creates 3D images of the body. It does this by using radioactive tracers, which are usually administered to a patient through intravenous injection. The tracers are made up of carrier molecules that are tightly bonded to a radioactive atom called an isotope. The carrier molecule can interact with or bind to specific proteins or sugars in the body. The carrier molecule that will be used depends on what the doctor is looking for. If she suspects cancer or is monitoring a known cancer's growth, she may use FDG, a modified form of glucose, which gets absorbed by tissues. When tissues absorb a lot of glucose, it may indicate a cancerous tumor. The radiation from the tracers poses little danger to the patient since they quickly pass out of the body. The isotope produces small particles called positrons, which interact with surrounding electrons. This interaction results in a complete annihilation of both particles, releasing 2 photons that speed up in opposite directions. The detectors in the PET scanner measure these photons and use this information to create an image of the distribution of FDG in the body.
Okay, so again, there are lots of imaging and need for this kind of information in nuclear medicine. Okay, so we've talked a lot about the physical properties of an atom, and now we want to shift gears a little bit and talk about the energy in an atom. And as it mentions there, this is now looking at page 7 of the course outline, looking at energy levels of electrons. So this is where we now start looking at electrons. They're very important in determining the energy of an atom. So what is energy again? We said energy is the ability to do work or cause change. And in the case of the cell, we're talking about cellular work, namely growth, reproduction, and metabolism, as we mentioned. So we have a term here, potential energy. This is an important concept. It's energy that matter has because of its location or structure. So as the name implies, it has the potential to do work. And so electrons of an atom differ in their amounts of potential energy. And an electron's state of potential energy is called its energy level. And we show these in diagrams with circles that we call electron shells. So that's where we're going next, and looking at how do we do electron shell diagrams, and how do we then explain how atoms come together to form molecules. So we look at the top diagram here, and you can see a good analogy here is a ball bouncing down a flight of stairs. It provides an analogy for energy levels. So if you put a ball on the top of the stairs, it just naturally wants to go down the stairs. And electrons are the same way, because as they bounce down the stairs, they release energy and become more stable. So here's something to remember. As you increase energy in a system, you decrease stability. They're inversely related. And so atoms seek some sort of arrangement that will have their electrons as close to the nucleus as possible, because there's less energy and more stability that way. And another reason the electrons like to be as close to the nucleus as possible is because the nucleus has what kind of charge? What kind of there are 2 subatomic particles in the nucleus, right? So there's neutrons, but also protons. So it's going to have what kind of charge? Positive. And if it has a positive charge and electrons have a negative charge, what do you know about opposites? What do they do? Opposites attract, just like magnets, right? The positive and negative ends attract. So electrons are attracted to the nucleus, and they're more stable there. They want to get as close to that nucleus as possible. But here's the problem. There's a limit to how many that can fit in all these different areas. And so we have these laws that deal with where electrons are going to be found in an atom. And the rules are that in this first shell, there's only 2 electrons that can fit there. So there is limit 2 here, and every shell after that can have up to 8. This is called the octet rule. OCT means 8, right? Octopus has 8, or an octagon has 8 sides. So we can have a limit of 2 in the first shell and then 8 in every shell after that. And that is called the octet rule. So when we look at electron distribution then, here's the electron shell diagrams, again, are going to be these circles, and we're going to show where these electrons are, and that's going to explain their stability and also the chance that they will form bonds with other atoms to form molecules. So when we do electron shell diagrams, the shell closest to the nucleus can hold a maximum of 2 electrons, otherwise up to 8 as I mentioned, and that's what we call an octet rule. So atoms seek an arrangement that will surround them with 8 electrons or have a filled shell, which means if they have 2 in their first shell, they're happy and they don't want to form bonds with anything else. If they have 8 in their second or any other shell, then they're still happy and basically unreactive. It's when they are missing electrons in their outer shell that they seek to either recruit some electrons from some other atom or give up some or even share some. So what causes these elements to form compounds? Why is it when you mix sodium and chloride you get table salt, sodium chloride? So I'm going to show this clip that'll talk a little bit about what causes them to come together, and then we'll do some electron shell diagrams.
But what causes elements to form compounds? And why do some elements, like the noble gases seen here in the periodic table, seldom join together? For example, neon, one of the noble gases and often used in advertising, is rarely found.
Let's start that over again, what that was all about. Unfortunately, we can't get rid of these.
But what causes elements to form compounds? And why do some elements, like the noble gases seen here in the periodic table, seldom join together? For example, neon, one of the noble gases and often used in advertising, is rarely found in a compound. For the answer to this question, we need to examine the structure of an atom and take a look at chemical bonding. Remember, each atom or molecule has a center called a nucleus containing 2 major particles, a proton and a neutron. While protons are positively charged, neutrons are electrically neutral. Then, whirling around the nucleus are negatively charged particles called electrons. These electrons move in paths that are arranged in energy levels. The outermost energy level is most stable when it contains 8 electrons. Whether an element is likely to bond, that is, combine with another element to form a compound, depends on the arrangement of electrons in the outermost energy level. If this outer energy level, known as the valence level, is filled with electrons, the element is chemically stable and will not bond. Chemists call the electrons in this outermost energy level valence electrons. Neon, like the other noble gases, has its full number, 8 electrons, in its outermost energy level. And because of this, all the noble gases are chemically stable.
Scientists use a dot diagram to represent the number of valence electrons in an atom's outermost energy level. Here, for example, are dot diagrams for the elements sodium and chlorine. According to the dot diagram, how many valence electrons does an atom of chlorine have? An atom of chlorine has 7 valence electrons. You can tell this by the number of dots shown in the diagram. While the noble gases have 8 valence electrons,
All other elements in the periodic table have between 1 and 7 electrons in their outermost energy level. In order to fill their outer energy levels, these elements will gain, lose, or sometimes share electrons, and by doing so, form chemical bonds.
Okay, so a good analogy for thinking about energy levels is thinking about rungs on a ladder. And let's say we have to climb a ladder and we are all acrophobic. What does that mean? Fear of heights, exactly. And so we all want to be on the first rung, closest to the ground, which is most stable. But we can't because there's only so many that can fit. And so there's a limit. And so some of us have to go to the second rung and the third rung. And those at the top of the ladder are the most unstable, most apt to fall off, right? Electrons are the same way. Those in those outer shells are most unstable and more apt to go somewhere else than those that are close to the ground or the nucleus. So the other thing to remember though is as long as they have the outer shell that is filled, then they are also stable. And how many does that? Most of the shells need to be filled. 8, right. So if we look at the electron distribution in this diagram for neon, which has 10 electrons, and by the way, in order to do electron shell diagrams, the first question is, how many electrons are we diagramming, right? How do we know it has 10 electrons? What do we look at on the periodic chart to find out the number of electrons? Atomic number, exactly. So the atomic number of neon is 10, so we're going to put how many in the first shell? 2, and how many in the second shell? 8, and that's a total of 10. So now the question is this a stable structure? Yes, it's already got its outer shell filled, and as that clip I just showed you pointed out, it is chemically inert, and that means it's not reactive. It's okay all by itself. It doesn't need anybody else. It is happy because it's stable. So let's do an electron shell diagram now for sodium chloride, table salt. And to do that, of course, we need the periodic chart because we need to figure out how many electrons are we diagramming. Now, when we do electron shell diagrams, the way I always do them is I put the nucleus and I put the chemical symbol for whatever it is I'm diagramming. In this case, it's going to be sodium. And I have to also write how many protons so I know how many electrons. So what is the atomic number for sodium? 11. 11 protons, which means we're going to have 11 electrons. So we draw our first shell, which can have a total of how many? 2. 1, 2. And then our second shell can have up to how many? 8. 1, 2, 3, 4, 5, 6, 7, 8. And that's a total of 10. And that leaves how many in the third shell? Just 1. 1 lonely electron. Is this a stable structure? Think about it. This is the top of the ladder, and also, how many more does it need to be filled? 7. So this is very unstable. This is not even close to filling its outer shell right now. But let's try another one. Let's do chlorine. This one you guys do on your own, just to make sure you know how to do these diagrams. On the first test, it is multiple choice, so you're not going to turn in any drawings, but you'll have scratch paper and you will have to do the drawing so that you can answer the question. So the questions might say, how many electrons are in the first shell of sodium, or the second shell, or the third shell? So for chlorine, so right here we're going to be diagramming 17 exactly, 17 electrons. So you have 2 in the first shell, 8 in the second, for a total of 10. And how many in the third shell? 7, exactly. 1, 2, 3, 4, 5, 6, 7. That's a total of 17. How many more does this shell need to be filled? Just 1 more. Well, guess what? Sodium's got 1 to spare. Chlorine needs 1. What if we take this electron and pass it over to this one, we transfer it, that would get rid of this entire outer shell, and sodium would be happy because now its outer shell is filled. Chlorine would be happy because its outer shell is filled. So this works for both, and this is one of the reasons that they like to form bonds. But here's what happened here though. Sodium lost an electron and chlorine gained one. Chlorine has 17 protons, but it's got now 18 electrons, giving it what kind of charge? It's no longer neutral. What's a positive 17 and a negative 18 come to? Negative 1. And sodium lost an electron. It's only got 10 electrons, which gives it what kind of charge? Positive 11 and minus 10 would be a positive 1. So sodium takes on a positive charge, chlorine takes on a negative charge. These are no longer atoms because by definition an atom is electrically neutral, right? So there's a different word for what we call a charged atom. Anyone know what it is? It's a small word, begins with an I. An ion. So this is a charged atom, it's called an ion, and guess what? What do oppositely charged atoms do, or ions do? Positive and negative, so they're attracting. And so that's exactly what happens here. So sodium and chlorine are attracted to one another, and that forms what we call an ionic bond. So an ionic bond is formed when we actually transfer an electron. This electron no longer goes back over to sodium, it only orbits around chlorine, which gives chlorine that negative charge. Sodium essentially lost an electron, giving it a positive charge, and they are attracted to one another. Now, if I asked you to do the electron shell diagram, well, first before I move on, is everyone okay with these shells? Anybody? Okay. So if I asked you to do an electron shell diagram for, say, uranium-235 or 238, you'd be drawing circles all day long, right? So rather than that, we can just look at our periodic chart, which has made this simple for us, and have set our elements up in according to group numbers that tell us the valence electrons. Valence electrons are the number of electrons in the outer shell. And that just then tells us right off the bat which ones are going to form bonds with which ones. And so when we look at this shell, for instance, we can see we just did the electron shell diagram for sodium. How many did it have in its outer shell? Just one, right? Notice what group it's in, group 1. If we did lithium, which has 3, it would have 2 in the first shell, 1 in the outer shell. It's also in group 1, and hydrogen only has 1 proton and one electron. It's the lightest element we have, and it's also in group 1. Chlorine had how many in its outer shell to begin with? 7. What group is it in? Here's chlorine, right? Group 7. It's got 7 in the outer shell. Fluorine also has 7 in the outer shell. Notice group 8 has how many in the outer shell? 8. So it is that group that doesn't really react. But group 1 would like to form bonds with what group? 7. Makes 8. Group 2 would like to form bonds with what group? 6. Makes 8. See how that works? Now, when there's small molecules like we see here, like sodium chloride is only made up of 1 sodium atom and 1 chlorine atom, it's easy to transfer like this. And also when you just have 1 electron involved, you're going to see it transfer. So we see these kind of bonds very common in groups 1 and 7 and transfer. But if I get to group 4, it's got 4 in the outer shell. How many more does it need to be filled? 4 more. Is it going to gain 4 or give up 4, right? So when you get in the center of the table, you're more apt to share. That is, the electrons are going to orbit around both. And that's a different kind of bond called covalent, which we'll get to later. But let me just use or define one more term for you, and then we'll get back to this idea of sodium and chlorine. So we have this term orbital, and we've talked about electrons orbiting around the nucleus. And by that, I don't mean circles, because we're showing circles. They're not actually circling, they're orbiting in a 3-dimensional shape. And so if you've ever had chemistry, you may have studied orbitals and suborbitals, and it gets real complex. We're not going to get into all that. Just if you know the definition, an orbital is a 3-dimensional space where an electron is found 90% of the time. We can't say for sure where the electron is because it's constantly moving. So that's just how we define an orbital. So, looking at then chemical bonds in concept 2.3, what is a bond? So we already talked about sodium and chloride forming a bond. It's when they're attracted to each other. So these interactions usually result in atoms staying close together, held by attractions called chemical bonds. This is concept 2.3, and now we are on page 8 of the course outline. So we mentioned this idea of ionic bonds. So ionic bonds are cases where there's an electron transfer. Something gains an electron, something else loses it. Folks, they go hand in hand. If you get a question on a test that says, are ions formed by gaining electrons, losing electrons, or both? What would the answer be? Both, right? Because anytime something loses an electron, something else gains it. When it loses an electron, it takes on what kind of charge? Positive. When it gains an electron, it takes on a negative charge. So they go hand in hand. This is an ionic bond. So to go back to sodium chloride, look at it again. This is what we just showed on the board. Here's sodium. It had 11 electrons. We put 2 in the first shell, 8 in the second for a total of 10, leaving 1 in the third shell, all by itself, very unstable. Chlorine had 17, we put 2 in the first shell, 8 in the second for a total of 10, that left 7 in the outer shell. It needs just 1 more to be filled, so we transfer it. This is a move, a permanent move from sodium to chlorine. And now sodium lost its entire outer shell, but now the second shell is filled, so it's happy. Chlorine gained that electron, and its outer shell is filled as well. But because sodium lost an electron, it takes on a positive charge, and we call this a cation. Think of this, if you like cats, they're very positive. Not really, are cats really positive? I don't know. I think they're finicky, but anyway, positive is a cation, and chlorine gained an electron, and it is called an anion when it has a negative charge. So cations and anions are always formed hand in hand, because something gains, something loses. And there you have sodium chloride. So that forms an electrostatic attraction, almost like when you brush your hair and your hair sticks to the brush in the winter. So that's because there's some electrostatic sort of stuff going on in the air. So these cluster together, and that's how we have salt crystals. And that is an ionic bond. Again, remember, this is common in small molecules like sodium chloride that only involve groups 1 and 7, just transferring 1 over to 7. So a cation is positively charged, anion is negatively charged, and an ionic bond is an attraction between an anion and a cation. And here's a clip on that.
Now we will learn about ionic bonds. Ions, as you already know, are formed from the loss or gain of electrons. Electrons, however, do not suddenly appear or disappear. They are in fact transferred from one atom to another. Let's look at sodium chloride as an example. Sodium loses 1 electron to form a sodium ion. The electron is not lost, but transferred to chlorine to form a chloride ion. So we have a sodium ion and a chloride ion. They are oppositely charged ions and will be electrostatically attracted to one another, much like how opposite poles of a magnet are attracted to one another. This electrostatic attraction is an ionic bond. Sodium chloride is an ionic compound because it is held intact by ionic bonds. The same thing happens with magnesium and oxygen. Why don't you grab a piece of paper and a pencil and draw the resulting ionic compound, magnesium oxide. Please pause the lesson and resume when you are done. Magnesium transfers its 2 valence electrons to oxygen, forming the magnesium ion and an oxide ion. The resulting ions are electrostatically attracted to one another, forming an ionic bond. Did you get this right? Did you remember to include the charges on the ion? Now, Let's look at calcium and chlorine. Calcium loses 2 electrons to form a calcium ion. One of these electrons is transferred to a chlorine atom, and another is transferred to another chlorine atom, forming 2 chloride ions. The calcium ion is electrostatically attracted to the 2 chloride ions because the opposite charges must fully balance each other out. In all 3 examples, the resulting ionic compounds have an overall neutral charge because all charges are fully balanced out. In summary, an ionic bond is defined as the electrostatic attraction between oppositely charged ions. When an ionic compound is formed, the charges must be balanced so that the resulting ionic compound has an overall neutral charge.
Okay, so to recap, 3 things that you need to do for this first test that you should practice. One is, given the periodic chart that you have in your course outline, figure out the number of protons, neutrons, and electrons in any one of those elements. And then once you get that written down, put the chart away and take what you wrote and figure, given the protons, neutrons, and electrons, figure out atomic number and atomic weight. So be able to do that both ways. And then the third thing is to do these electron shell diagrams. So everybody, anyone have questions so far about any of that? No? All right, good. So we will stop there. You guys have a great holiday weekend. I will see you Tuesday. Don't forget to dress for lab. And if you have any questions, come on up. Otherwise, have a great weekend.